In this section, we're going to look at how we can evaluate some more difficult integrals using a technique called substitution, or a lot of times we call it U-Substitution. So here are some basic integration formulas that we've already memorized from our study of integration. But now you can see instead of having an x inside of these integrations, we have a u. So in these formulas, the variable u represents some function of x. And then du is the derivative of u with respect to x. So we use u-substitution to find the integrals of functions that have had the chain rule done to them. So u-substitution is like the reverse of differentiation using the chain rule. So this means that there's going to be an outside function and an inside function. And so what we do is we let u represent the inside function. And this allows us to find the integral with respect to u, and then we can plug back in the value of x. So we can write our final answer in terms of x and not in terms of u. Now let's look at a basic integral. Say we want to take the integral of x to the 7th power. Then we know using the power rule for antiderivatives that the answer would just be x to the 8th divided by 8 and then plus our constant of integration c. But what if instead we want to find the integral of 3x minus 4 to the 7th? So now this is kind of like where we have an inside and outside function. 3x minus 4, that's the inside function, and then we're raising it to the 7th power. So you can see it's pretty similar to what we had up here, except instead of an x being raised to the 7th power, we have a whole another thing, 3x minus 4 being raised to the 7th power. So we could try to take the integral of this just straight up, just using our power rule for antiderivatives, so we could see what would happen if we tried to do that. Now our intuition should probably tell us that that would not be the correct way to do it, but let's just see what happens. So if we just use the rules we used up here, then we would get this as an antiderivative. Basically, it's just exactly what I have here, but instead of the x, I have the 3x minus 4. So to find that, I basically just used the power rule for antiderivatives, the one I used right here, and didn't really do anything with that inside function. I didn't account for it in any way. So let's check and see if this is the correct answer. So to check and see if this really is equal to the integral of this, we would just want to take the antiderivative, or we just want to take the derivative of our answer and see if it equals what was inside the integration sign. So taking the derivative, we have to use the chain rule, and so when we do that, we get the derivative of this guy right here is equal to this, which is not equal to this, which is supposed to be. Remember, if we find the antiderivative, then if we take the derivative of the antiderivative, we should be back to where we started, and we're not. We have this extra 3. So we're close to the right answer, we're close to the right antiderivative, but it's not quite right. So the reason it's not quite right is because we didn't account for this change. The fact that we didn't just have an x to the 7th power, we have 3x minus 4 to the 7th power. So we need to do something to account for that change. So to correct, let's make a substitution. Let u equal the inside part. So then we're going to be able to write the integral of u to the 7th power du, because this 3x minus 4 right here, all that got replaced with u. So then we can write our integral like this. But we need to figure out what du equals. We want the integral of u to the 7th power times du to be exactly equal to this integral that we're trying to find, this one. But you can see I put a question mark here because we don't know if these two guys are equal. So we know for sure that 3x minus 4 to the 7th equals u to the 7th because 3x minus 4 is exactly u. So we know that these guys are definitely equal to each other. So this one's good. And we know the integration sign, this and this, they mean the same thing, so that's no problem. So the only problem we have is, does dx equal du? That's what we don't know. So we need to try to examine those and figure out whether those two things are equal or if we need to make some kind of additional substitution to account for the differences in their values. So we need to figure out what du equals, or really kind of what dx equals, because we want to replace dx with something that has du in it. So the way we do that is we take this equation, u equals 3x minus 4. Now we take the derivative on both sides. So we have du dx equals the derivative of the right-hand side. Now the derivative of the right-hand side with respect to x will just equal 3. So we get du dx equals 3. Now what we want to do is solve this equation for dx. So we did a little work with these guys, the du and the dx. We call them differentials. We did a little work with them in previous sections. So you can kind of think of them as their own expression. So what we can do is multiply both sides by dx. So then on the left-hand side, the dx's will cancel, and you just have du. And on the right side, we have 3 times dx. But we're trying to solve for dx, so let's divide both sides by 3. So then we have dx equals du divided by 3. So now we know the relationship between dx and du. So now we can take that value and plug it in for dx. And that will allow us to have an equivalent expression. Now, if you can see, we had this question right here. We said, is dx equal to du? So now we know the answer is no, it's not equal. The true equation is dx equals du divided by 3. So that will be a true equation. So let's plug in the value of dx here in our integration. So I have this integration equals the integration of u to the 7th, just plugging in u for 3x minus 4. And now dx, I know that equals du divided by 3. So I replace dx with du divided by 3. So now I know that these two, that this equation is true. So the thing that was missing before was that dividing by 3, and I found out what that was by doing this analysis over here. I took the derivative of u, and that gave me the opportunity to solve that for dx, because I had those differentials as a result of taking the derivative of u with respect to x. Now I can rewrite my integral as the integral of 1/3 times u to the 7th du, and I even could put the 1/3 on the outside if I wanted to. So now I use the power rule to take the integral of u to the 7th, and I'll just get u to the 8th divided by 8. And then of course I have that 1/3 on the outside, and then I also have plus my constant of integration c. So that gives me u to the 8th divided by 24 plus c. And now I can plug back in the value of u with respect to x. So I replace u with 3x minus 4, because that's what I know u equals. And so now I have the answer to my integration, and my answer is dealing with x. So I finally have my answer. The integral of this guy that I started with way up here is equal to this. And so you can use U-substitution to find that answer. And so now if you take the derivative of this thing that we've got down here at the end, the derivative of that would equal 3x minus 4 to the 7th, like it should. So this is how we do U-substitution. The reason we want U-substitution is because we wouldn't know how to take the integral of the thing we started with for this example unless we used U-substitution. So it allows us to take the integral of some more complicated expressions.